So let's look at this interesting one. It looks like a rational function, except we end up with a radical in there, which is going to make this look a little bit different. Again, let's talk about the domain, since it is, we can do it down here. The domain of this function, we have to look to see where the denominator could be 0 or undefined. And so, again, we've got two things that we need to worry about. One is dealing with the square root. We don't want any negatives under the radical. And the second is the fact that this is the denominator. We don't want a 0 in here. So if we just take and look at x squared plus 2. Right, so we would say, well, I can't have that be negative, so it has to be greater than 0. And I can't have it greater than or equal to 0, and I can't have it be equal to 0 because it's in the denominator. So I want x squared minus 2 to be strictly greater than 0. Right, well, if we just look at this, x squared is at the very minimum going to be 0, and then we're adding 2 to it. Again, usually this will be greater than 0 unless we put 0 in there. So, but then we add 2 to it, and this will always be greater than 0. So in this case, there are no restrictions to our domain at all because of the fact that that will always be positive. So domain, let's put that down here, is all reals. Or you could just say negative infinity to infinity. Okay. So then our first derivative, let me just rewrite this as x over x squared plus 2 to the 1/2, just for the derivative purpose. All right, first derivative. And again, I encourage you to turn off the video and just do this on your own so that you get the practice with it. Okay, so then we have bottom times the derivative of the top minus the top times the derivative of the bottom. So that's x squared plus 2 to the negative 1/2 times 2x all over the bottom squared. So it's going to be x squared plus 2, actually just to the first. Okay. We have this 2 and this 1/2 that's going to cancel. We'll eventually group these two x's together to get an x squared, but right now what I'm noticing is that I have a negative fractional exponent. So let's simplify this by doing our little trick where we just multiply top and bottom by x squared plus 2 to the positive version of that. So x squared plus 2 to the 1/2 times x squared plus 2 to the 1/2. That is going to give us, when we multiply this by x squared plus 2 to the 1/2, it's just going to give us an x squared plus 2 minus, when we multiply this by x squared plus 2 to the 1/2, these will cancel, and so we're just going to get an x squared. And then in the denominator, we've got, basically this is 2 halves and 1/2, so we'll have x squared plus 2 to the 3/2, which will end up becoming, when these cancel, 2 over x squared plus 2 to the 3/2. That's our first derivative. And I'm going to change this for the sake of taking the derivative to 2 times x squared plus 2 to the negative 3/2. All right, so that when we take the second derivative, we don't have to use quotient rule. We're just use power chain rule right here. All right, so second derivative, f double prime of x is equal to, we bring down that 3/2, so we end up with negative 3 times x squared plus 2. We decrease that power by 1, so to the negative 5/2, and then the derivative of the inside, which should give us 2x. And we end up with negative 6x times x squared plus 2 to the negative 5/2, or probably we'll write that as negative 6x over x squared plus 2 to the positive 5/2. All right, so there's our second derivative. All right, x-intercepts. This is where is the y value equal to 0? And again, in a rational, semi-rational function like this, that means set the numerator equal to 0. Right, so the x-intercept is going to be just 0, 0. Which means that the y-intercept is going to be the same thing. All right, vertical asymptotes. Again, we already looked for that, and we said that there are none. Horizontal asymptotes. This is like the ones that we've seen in the textbook where we end up with a square root in the denominator. And the shortcut for this is that if we just think about the fact that, again, let me steal some space from up here. This is x over, again, as we are getting out to positive infinity, this right here is negligible. All right, and so really it's x over square root of x squared. And as I'm heading towards positive infinity, I know that the square root of x is just x. And so we end up with x over x, which is 1. So we will get a horizontal asymptote at x equals 1. But again, let me go back to this. As x goes to negative infinity, remember the square root of x squared as x is approaching negative infinity is x over negative x, or the opposite of x, which is negative 1. And so we get a second horizontal asymptote at x equals negative 1. Again, that will happen when we have a square root in the denominator like that. Okay, critical numbers come from where is the first derivative 0 or undefined. Again, the denominator is never going to be 0, so we're not going to get any critical numbers from the undefined part. And then we can't get any zeros from the numerator because it's just a constant, so there are no critical numbers. In other words, there's not going to be any max values or min values. All right, possible points of inflection, again, that comes from where is the second derivative 0 or undefined. Again, the only place it's 0 is where the numerator is 0, so possible points of inflection, x equals 0. Okay, we already did the domain. Symmetry, let's find f of negative x. Again, that's always what we do because when we want to see if it's equal to negative f of x or is it equal to just f of x or something in between. All right, so I'm going to plug negative x into our original function. So I've got negative x over square root of negative x squared plus 2. All right, so I end up with negative x over, in the denominator here, I just get x squared plus 2 again. Well, this is, again, if I pull this out front like this, maybe that'll make it more obvious. This is f of x right here, so this is negative f of x, which means that this function is odd. In other words, it has origin symmetry. Okay, hopefully you're tracking right now. So test intervals, again, that comes from any vertical asymptotes, any critical numbers, and any possible points of inflection. Right, there are no vertical asymptotes, there are no critical numbers, and we only have one possible point of inflection, and that is x equals 0. It's going to be a pretty tiny table. All right, we only have to the left of 0 and to the right of 0, and then we're going to have to test at 0. So, next page, it's a very small table. And I'm going to leave this one here with us because we're going to need to graph in just a second. Okay, it is going to be negative infinity to 0, x equals 0, and 0 to infinity. And again, we do not find the values of the original function on an interval. We can only do that at individual points. All right, so at x equals 0, I'm going to have to kind of do this at the same time. So when x is 0, we go into our original function. Oh, we already know that this is 0 because 0, 0 is the x and y intercept. All right, so for f prime of x, I'm going to choose, actually in this interval, I'm going to choose -1, and here I'm going to choose +1. So f prime was this. All right, so if I put -1 in here, again, always positive. This x squared plus 2 is always positive. I cube it, it stays positive. I take the square root, it stays positive. And the numerator is always positive. So this ends up being positive. Oh wait, I forgot to say how 0 ended up in here. This was a possible point of inflection. Right. When I plug 0 into f prime, I end up with, this is 2 over 2 cubed, which is 8, the square root of that. All right, so this is, actually, it doesn't matter. We're just looking for a sign. It's all positive. All right, and then I plug in 1, and I end up with something positive. All right, then I do f double prime. This things will be interesting because that is what the second derivative is. So when I plug in -1, that becomes positive, and this is positive, so positive. When I plug in 0, I get 0 over positive, so 0. And then when I plug in 1, I get negative over positive, so negative. Okay, let's say what's going on here. So again, this is going to tell whether something's increasing or decreasing. This is going to tell if it's concave up or down. So here we've got increasing, concave up. This ends up on here because it's a possible point of inflection. And again, for points of inflection, we look to see, does the concavity change from up to down? And yep, it does. So this is a point of inflection. Again, at this point, we thought it was a potential point of inflection or possible point of inflection, but this confirms it, that the concavity changes around it. Here it's concave up, here it's concave down, so it must have changed there. That's a point of inflection. And here it is increasing and concave down. Right, so again, it's unfortunate that I have to keep squishing all this stuff in here. So let's have the graph and this in here. So the points that we need to plot, literally just 0, 0. That's all we've got. We also know that there is a horizontal asymptote at 1, and there is a horizontal asymptote at -1. We also know that it's symmetric about the origin. So whatever happens in this quadrant right here is going to, the same thing's going to happen down here. All right, so let's see what goes on, and vice versa. Whatever goes down here, the opposite's going to happen in here. So we know that from -infinity to 0, it's increasing and it's concave up. And we also know it's got to hug either this asymptote or this asymptote. In fact, as it went to -infinity, it hugged -1. So it's got to look something like this, increasing and concave up. And then it's a point of inflection, so it's got to switch. Now it's increasing and concave down, and so it's going to look something like this. All right, again, it might be nicer if we had maybe not the numbering that we do, so let me just draw it in another spot so it's easier to see. It's going to look something like this. All right, that's basically what a cube root looks like. And again, we've got these asymptotes right here. It's hard to see when it's so narrow right there, but maybe this will help a little bit where actually, I don't know that I've spaced it out that much. Anyway, that is what it should look like. Okay, that is it.